process. Okay, let me just get rid of the recording in progress box. Excuse me, because my cursor is, sorry, I'm just going to briefly try and get rid of this box because, right, sorry. Yeah, apologies for this, but my cursor disappeared when this, right, fine. Can you still see my slides?
Yes.
Okay. Yeah, great, thanks. Yeah, so, and then the other issue is that high-level content, for instance, high-level objects such as jets, and then elements of working points and so on, which are often updated as knowledge of the reconstruction improves over time, don't get updated very often because, as I said, reconstruction data is rarely updated. So for this reason, we have these reduced formats, and they have certain properties that are usually in common. So they are almost, well, let's say usually produced in bulk centrally and made available to analysts in officially documented data sets. They usually contain the high-level content that might get updated or improved for a given version of the reconstruction. I think they always contain the variables required to apply calibrations and evaluate instrumental systematics at the analysis level. I think they are always smaller than the reconstruction output, or there wouldn't be much point in having them. And now sometimes, and this is particularly for the Atlas case at the moment at least, or in run 2, they are skimmed, so they don't contain all of the events. They are sometimes tailor-made to specific analyses or groups of analyses, and they are sometimes written with the same event data model as the reconstruction output, but not always by any means. And finally, they are usually used as the input for n-tuple production jobs, the output of which is then used for direct analyses. So just to, I know that different experiments can sometimes have different nomenclature. So just to say what we use in Atlas. So when we say skimming, we're talking about the removal of whole events on some preset criteria. When we're discussing thinning, we're talking about the removal of whole objects within events, again, based on some preset criteria. So, you know, remove all tracks less than 10 GeV or something like this in PT. And then when we're discussing slimming, at least in Atlas, what we mean is the removal of variables within objects uniformly across all events. So I think there's sometimes the slimming and skimming as sometimes, or thinning and slimming are sometimes used interchangeably, but these are the three definitions in Atlas. So in run 2, Atlas had this model where we had around 100 different derived AOD or DAOD formats, which were specifically tailored to individual analyses. So of course, the reconstruction output is very large. It has, there's one format, it's written for all events, and it's written in the common XAOD Atlas EDM made in the central production. And in the reconstruction, you're essentially building the low-level objects from the raw data and some of the higher-level objects. So these DAODs, as I said, there are around 100 of them. They were skimmed in run 2. So we typically tried to write not more than, say, between 1% and 10% of the events, with a strong preference towards the lower end of that range than the higher end. Per event, they were typically something like 30 to 50 kilobytes because and the per event content was very much the same across all of these different formats. On the other hand, some of them were much bigger because they required specific branches for very specific purposes. And again, these were written with the XAOD EDM. In other words, they had the same look and feel as the output of the reconstruction. This again was done with central production, and at this stage we would write high-level objects such as most of the jet and flavor tagging MET containers, and also of course the data reduction operations would be done. And then finally, on the basis of these outputs, the users would be writing their n-tuples, of which of course there were thousands, many per analysis, many per analysis in some cases, and these would usually be written with a flat root structure. This would typically be done with user grid jobs or analysis jobs submitted by a team, and at this stage calibration and systematics would be applied. Now in run 3, things are going to be a bit different. The majority of analyses, we hope around 80% of them, will adopt something called DAOD FIS, which will be a single format written for all events, data and Monte Carlo. It will contain this common set of variables which are needed by most analyses. So it will be per event around the same size as most of the old style DAODs of around 30 to 50 kilobytes per event, depending on the whether it's data or Monte Carlo and the pileup. We still need some of the old style DAODs because the combined performance work, in other words, actually setting the calibrations, requires more variables than are available in DAOD FIS. And also certain special analyses, which I'll mention a bit later, are also needing to have these variables that aren't available in FIS. Then we're going to introduce a second new format called FIS Lite. I'm going to discuss this on the next slide. This will be the prototype for run 4, but it will be progressively introduced during run 3. Now, the idea of this format, again, there's just one of them. It's written for all events, but we hope that this will be something like 10 to 12 kilobytes per event. Again, it will use the common EDM, the XAOD. And in run 4, it will again target around 80% of the analyses. One of the main aspects of this format is that we hope that it can be directly analyzed without the need for entupling. So I'll say a bit more about these formats individually in a second, but I'll first of all explain why we changed from this many DAODs model to having a far fewer. And the basic reason for this is that the run 2 model took up too much disk space. The DAODs were supposed to be primarily reduced by aggressive skimming, but this was a lot less successful than hoped because the skimming tended to be looser than we might have hoped, because there was some uncertainty about whether one could afford to skim more tightly, particularly those based on high-level variables. And then when it came to the large standard model background Monte Carlo samples, these tended to have very high skim fractions. And this meant that the event-wise overlap between the formats was very high for simulated events. And because most of the formats had very similar content on an event-by-event basis, this meant that at least for Monte Carlo, many of these different DAODs were just writing out the same events again and again. So taking advantage of this situation, we moved to a model where we would just take this common set of variables that were being used by more or less everybody, write them into a single format for all events, and this gives us DAOD FIS. So DAOD FIS, as I said, is unskimmed. We hope it will be in the range 30 to 50 kilobytes per event, depending on whether it's data or Monte Carlo and the pileup. And it contains the full set of high-level objects and variables needed for analysis tasks, including calculation of instrumental systematics. We managed to get the size down by making aggressive thinning of inner detector tracks and vertices, which aren't normally needed for most physics analyses, by significantly reducing the trigger information and replacing it with a simplified matching scheme, and replacing the Monte Carlo truth record with a much smaller truth classification summary. The look and feel of this thing is quite similar to the run 2 DAODs. And you can see the breakdown of the different contents in the pie chart. Now, DAOD FIS Lite, which, as I said, will be introduced progressively in run 3, is again unskimmed. So it's written for every event. But the key point here is that all of the calibrations are pre-applied, such that many of the supporting variables that we have in the FIS format can be dropped because we already apply these calibrations as we're making it. And consequently, we're able at the moment to reduce the size to something like 10 to 12 kilobytes per event or less. And this significantly simplifies the analysis workflow. And in addition, although we're using the XAOD EDM, because this can be read directly in root, it should be in principle possible to avoid n-tuple making and allow analysts to process this format directly in our data frame or uproot. So the pie chart again gives the breakdown of the contents, and I will just highlight that you can see here that we have the breakdown between calibrated and uncalibrated variables in the inner pie chart. So how this all fits together. So of course, FIS has to be made from the AOD. A detail, a rather important detail, is that in run 3, we're going to keep AOD on tape primarily, with the disk used as an operational cache, and this is called the data carousel. So we can make both FIS and FIS Lite from AOD, but importantly, given that detail of the operation from tape, we can also make FIS Lite from FIS. And because FIS is on disk, this means that we will be able to make FIS-Lite more frequently because there'll be less data movement involved. Now you'll notice that I've shown the arrows giving the different tasks that are done as we build these different formats, and you'll notice that I don't mention systematics for FIS-Lite, and I'm going to come to that in 1 or 2 slides time. You'll note that I didn't, that I kind of brushed over the fact that 20% of the analyses won't be able to use these new formats. We expect that we're going to have to use the Run2 style DAODs for the combined performance groups who have to be able to derive calibrations and systematics, and also special analyses, such as those that require tracking information. This is especially relevant to BFIX and long-lived particle searches. The residual DAODs will be produced coherently with FIS and FIS-Lite to make maximum use of each staging from tape. And what we're hoping, and the numbers seem to bear this out, is that with reasonable assumptions on the number of data and Monte Carlo events for Run 3, we estimate that the DAODs together, that's FIS, FIS-Lite, and these residual formats, will be around 50 to 70% of the size of the AOD versus around 100 to 120% today. It's still the case that the bulk of this will be taken up by these residual formats, which are mainly needed for these combined performance studies. There are some new ideas on file augmentation that may hopefully render some of these residual formats redundant. And in the table here, I'm just showing how many replicas of these different kinds of analysis format we'll keep. At the baseline, we will keep 4 replicas across the grid of FIS and FIS-Lite to ensure that there's plenty of coverage, and if we need to make more replicas dynamically, we can do so. I'm not going to say much on this idea of file augmentation because there's going to be a discussion of this from Lucas and Jackson later on. Needless just to maybe highlight or preview this, the idea is here that for formats, dedicated DAD formats where there's relatively sparse event selection, we may just be able to decorate the existing FIS format with extra trees so that it's possible to retain the common content and then have additional trees attached to this containing the extra quantities, meaning that we don't have to write out a whole new DAOD formats. But I'm going to leave that, given I haven't got much time left, I'm going to leave that to Lucas and Jackson to discuss later on in this session. And then the other big important thing that needs to be worked on are systematics with FIS-Lite. So the current prototype of FIS-Lite writes the central values of the calibrated objects and some additional variables to derive systematics. And ideally, we would like to be able to drop this extra content and be able to derive the systematics from an external source. And by external source, I mean something like a lookup table, a parameterized form of the systematic instrumental variations, or potentially some machine learning model. Now, this is currently being explored with the aim of being able to calculate systematics without storing supporting variables by the time we get to Run 4. If we're able to do this, we should be able to drop more of the format. This is illustrated by these diagrams at the bottom. So in summary, Atlas is in transition from a model where many dedicated analysis formats are used to a model where the large majority use a single standard format. And this format is already in production and will be the baseline for Run 3 analysis. And then a smaller pre-calibrated format called FIS-Lite is being prototyped, which will be the baseline for Run 4. Actually, it is also in production at the same time as FIS for testing purposes now. And it will hopefully avoid the need for n-tuple building and should be the input to what we call columnar analysis. A widespread adoption of this format should ensure that Run 4 analysis remains tractable for physics analysts. Both of the formats will continue to use the Atlas common XAOD EDM. This will in time adopt the new R-n-tuple structure from root once it's ready, which will replace the T-tree. And with that, I'm sorry I maybe went a couple of minutes over. That's all. So thank you very much.
Thank you so much, James. Are there questions? Maybe we can start on Zoom. Questions on Zoom? No hands. Questions in the room?
Hi, thanks for the talk. I just have a quick question on the systematics. So you say we might want to add the systematic variations into the fizzlight. And from what I understand, right, systematic variations can change, like systematic prescriptions can change quite a lot or quite fast.
Mm-hmm.
So would that require us to produce fizzlight files multiple times quite quickly? And is that possible?
Well, yeah, I mean, the FIS light can be produced from FIS directly, and it's a very small format. So the actual computational overhead for making FIS light is pretty small. It's no bigger than a sort of a standard analysis job running, really, because the input is already a reduced format, which is FIS. So in principle, there's no problem in creating a fairly frequent updates of FIS light. Now, I'm not sure whether what you're asking is, will we actually have to have multiple concurrent versions at the same time supporting different systematic schemes? If that's what you're asking, the answer is we hope not. We hope to be able to really try to stick to one version. In terms of, are we able to, if say some prescription is updated from, say, the JET or missing energy group or something like this, then yes, we can quite quickly reproduce the whole lot. This is computationally quite a light operation. Did that answer the question?
Yes.
So it's super interesting to see the train of thought on slide 8, I think. We can't see the screen anymore, unfortunately, but don't worry about it.
Sorry, I'm not sharing anymore. Oh, yeah.
Don't worry, that's okay. So it was just the fact that you foresee sort of 80% of the physics program going to this one stream. This is nice. It also the way in which the skimming kind of turned out to be a bit of an issue because you have like a large overlap, and there's a lot of people are very loose. This is basically exactly what LHCb ended up stuck with in run 2. So as you probably know, we kind of went a slightly different route in that we just dropped the full reconstruction step for quite a lot of our analyses. And I was trying to work out from what you were saying about the systematics determination, if that is something that you could eventually target. So if you are able to control and to determine your systematics from alternate streams, which I think was your end goal, then is it the case that you would foresee just dropping the full reconstruction except for calibration and a few other streams where you need to like monitor the raw event data and just not have AOD, just go straight to a reduced data format from the output of the trigger?
I would be quite surprised if we could get away with that in a kind of with such a wide range of analyses, all the way from B physics to exotics searches. Certainly there are no plans in Train to skip the AOD step and go to a fully streamed model. Maybe in run 4 is a long way away, right? So we've got another 7 years of evolution of these models. So maybe by the time we get there, that maybe we will have decided that that's the best way to go. But as things stand, I can't see that being practical for Atlas. But I could be wrong, right? We have to, we were very wrong about the skimming model. We were very wrong about quite many things that we thought we knew in run 1. So let's see where we're at by the time we get to run 4.
I mean, the same is true for every experiment, right?
Yeah, exactly.
We're all learning this. But just so I understand, whenever you say you don't think this would work for sort of all of the breadth of use cases, is that the breadth of use cases contained within the 80% you're already putting on this new format, or is it the 20% that's the problem?
It's the 20% as well. So we have to be able to support B physics, long-lived particle searches. All of these run from AOD, or let's say there are maybe a few edge cases where they have to have a special construction set up. We have an extra format that's built as the raw is reconstructed, but almost all of the analyses that I'm talking about, including this 20%, come from AOD. And in addition, there's also the question of the combined performance group setting the calibrations, figuring out exactly what the instrumental systematics would look like. This all requires the AOD as well. And this is why we have to have these additional supporting remnant DAODs, which are used by, the JET group, muons, in the detector tracking, tau, etc. who need more variables than are available in the FIS format, but generally the AOD is sufficient to support this. So again, I think we're going to need the AOD for the foreseeable future.
Thanks.
Okay, I think we need to move on. Thanks again, James.